In this video, we'll be demonstrating the aerodynamic design of an axial, low-pressure fan, including a CFD simulation. First, you create a new project choosing the ventilator design module. Insert the design point of the fan. The design point is defined by volume flow rate, total pressure rise, and rotational speed. In this case, the fluid is air at 20 degrees Celsius. You can choose any fluid properties by choice, or by applying a fluids database. We can switch the rotational direction or add an inflow swirl if required. On the right side, you'll see the specific speed and the general machine type. Now we add a new component, selecting the axial impeller option. The main dimensions window opens. In this example, we use an unshrouded, standard impeller. We have two general options for blade design, airfoil or meanline mode. Here we have chosen the airfoil method. In CFturbo, there is also an option for multi-stage design, including contra-rotating impellers. This time we won't use it. It will be in a separate demo video. To calculate the impeller main dimensions, CFturbo uses numerous empirical correlations in the parameters section. In most cases, non-dimensional approximation functions are taken from textbooks, research papers, and our own data. Here we use the work coefficient to calculate the impeller diameter and a diameter ratio function to get the hub diameter. Additionally, several empirical efficiency correlations are implemented too to get reasonable initial values of the impeller main dimensions. Now the impeller main dimensions have been computed. On the right side of the window, you see important physical values, a sketch of the meridional section, the Cordier diagram, and initial velocity triangle on inlet and outlet of the impeller. In CFturbo, all geometrical parameters can be adjusted manually if required. Here we modify hub diameter and impeller diameter slightly. This will only have a minor influence on subsequent design steps. The meridional view allows the design of the meridional contours of the impeller. On the right side of the window, there are diagrams for area progression, static moment, and curvature, which can assist you in shaping the meridional contour of the impeller. All Bezier points can be modified numerically by changing numbers in the pop-up window. The user can adjust axial length of the impeller, as well as shape and position of leading and trailing edge. Now we add hub solids. For example, we can split the curves or transform them into Bezier splines. For demonstration purposes, we're choosing a very simple model of the hub contour. This tool is very flexible for modeling hub and shroud geometry if applicable. In the blade properties, at first, we set the number of blades, which is an input value with strong effects on the blade profile geometry. Then a method must be selected to calculate the radial equilibrium from hub to shroud. The meridional and circumferential velocity components can be adjusted to balance pressure and centrifugal forces. In the profile selection window, the user selects blade profile. It could be done from a NACA profile catalog or by point-based data. User-defined blade profiles can be easily implemented. For this demo, we have selected a NACA 6509 profile. On the right side, there are several diagrams with aerodynamic values and criteria to evaluate the profiles, for example, solidity or de Haller criteria. If required, the profile properties like stagger angle or chord length can be adjusted manually. In the next window, there is the actual status of the blade profiles, showing more detailed information of the current design. For example, we can evaluate blade thickness, blade angles on leading and on trailing edge, blade passage area, a blade-to-blade view, and so on. For NACA profiles, there is a possibility to set a finite thickness on the trailing edge of the blade. It is a trade-off. Blade sweeping is a possibility to deform the blade profiles in meridional and in circumferential position. It is mainly done to get better acoustics. Axial fans can become quieter this way. The empirical, so-called acoustic benefit is shown on the upper right side of the window. However, usually this goes along with some losses in efficiency and performance. Now we can see the impeller in its actual state in our 3D viewer. On the left side of the window, you have the model tree with all components and subcomponents. This allows for easy navigation, renaming, and graphical adjustment. The user can modify color and translucency for each component or subcomponent. To prepare the CFD setup, first we add an inlet extension, including a simplified hub nose. For this purpose, we apply the stator module of CFturbo, which can be used to make vaned and unvaned turbo machinery components like pumps or guide vanes. The inlet pipe should have a certain length in order to prevent an impact from the boundary conditions to the fan stage itself when running a flow simulation. In our example, we want to create a simplified hub nose which will be placed directly upstream of the impeller. We split the hub curve, change the curve type to Bezier, and create a rounded shape of the hub nose. Every single Bezier point can be numerically defined as shown for the Bezier point on the z-axis. As done before, for the impeller we have added a solid shape for the material domain of the hub nose and additionally for the outer diameter. Now the model will be shown in the 3D viewer again. Both components can be shown or hidden. Solid models of the whole impeller, including blades and blade fillets, or of the stator components, can be exported into any CAD format or meshing tool for CFD, CHT, or FEA analysis. Direct export to rapid prototyping via STL is also possible. In the same way as on the inlet side, we should add a pipe or a diffuser downstream of the impeller. Here we add an axial stator. Again, the stator should have an appropriate length. A recommendation for an outlet pipe length should be 5 times pipe diameter or more. As before, hub and shroud solid will be generated. Our model here uses the inlet pipe and the outlet pipe just for numerical reasons to run the 3D CFD simulations correctly. Of course, a user can create more complex geometries like guide vanes or bends upstream or downstream of the fan impeller. Even a virtual test rig could be prepared to compare 3D CFD data and experimental results later. Just like in the previous design steps, the model can be shown and updated in our 3D viewer. The final design step would be model finishing in CFturbo, including fillet design. Model finishing means a geometrical operation to create solid models for the fluid domain and for the material domain in excellent quality. This finishing is a precondition for many geometry export formats. It will be used often, but not for all CAD or CFD systems. For some of the export formats, the model finishing will be done automatically. Let's save the model before we export the geometry and prepare the simulation. We open the export window. CFturbo has export formats to all major CFD codes and CAD systems, as well as neutral formats like STEP, STL, or Parasolid. This fan model will be exported to Simerix MP. We have to choose settings for meshing and simulation. For this demo, we intentionally generate a very coarse mesh. We've chosen mesh settings which will create a mesh of about 500,000 nodes only. It will become a hexahedral binary tree mesh. For single-stage turbo machinery CFD simulations, we recommend 2 to 10 million nodes, depending on the number of blades and complexity of the secondary flow path. In the solver settings, we must define the number of iterations or time steps, and we have to choose between steady state or transient simulation and select a differencing scheme. To export the model to Cimerix MP, STL files are generated. Then the computational model will be exported, including boundary conditions. The user has the option to export mesh and solver settings. Or, as it is shown here, they can start the meshing process and the CFD software directly. By choosing this option, Cimerix MP will be launched and the meshing process will be done. Cimerix MP is an affordable, fast, and robust general-purpose 3D Navier-Stokes solver. CFD simulations with Cimerix MP provide realistic results that compare accurately with multiple field tests on various types of rotating machinery like pumps, blowers, compressors, and turbines. Now the model is ready for simulation. All boundary conditions are set for the design point. The project file will be saved before the simulation starts. Besides residuals, we can observe the flow field in real time. We can start dynamic streamlines or particles, show isosurfaces, or important physical values of the flow field on all surfaces or on sections. Compared to others, the Cimerix MP CFD solver is extremely fast. Steady-state and transient flow simulations can be run easily on a laptop. This steady-state simulation took just 3 minutes on a laptop with an Intel i7 processor. For models with larger mesh sizes, such as for multi-stage machines, there are options for distributed parallel computing available to fulfill higher computational requirements. Additionally, we're able to monitor physical properties in integral values like total pressure of impeller or stage, hydraulic efficiency of impeller or stage, shaft power, and torque. All results can be exported to Excel or other formats for further post-processing. In addition to starting the simulation manually as it is shown here, batch mode runs can be prepared to run performance curves or maps. We see here a converged solution for the steady-state simulation. We always recommend doing transient flow simulation to get a higher level of accuracy in your predictions. We always recommend 3D CFD simulations to evaluate turbomachinery components designed in CFturbo. In recent years, it has become more and more affordable to combine turbomachinery design software and CFD codes with optimization algorithms due to lower computational cost. In case design adjustments are necessary, after evaluating the simulation results, you can go back to CFturbo and modify the fan interactively. Here's a 3D printed prototype of the impeller we just created. It was exported directly to a 3D printer from CFturbo. There's no need to use an external CAD system. This high-quality impeller prototype made of nylon is fully functional. It's ready for testing. As you've seen, CFturbo is a user-friendly, straightforward solution for axial fan design and 3D CFD simulation. To register for a free trial and to learn more about our engineering services, visit cfturbo.com.